I just want to welcome you here to our masterclass at A Mind for All Seasons. And today we're really taking a deep dive into one hormone, insulin. And insulin is something that I think is grossly underappreciated. And so I hope by the time we get to the end of this, you have a much greater appreciation for what this humble hormone, as Dr. Ben Bickman would put it, that's made in the pancreas is all about, and just how profound an effect it has on our entire bodies. And in knowing something about this, you'll know some things that you can leverage to further optimize your health and the health of people that you're serving. So let's dive in. It almost goes without saying, but I want to call out right up front the fact that all of us, everyone on this webinar, everyone that watches the replay, every single person who has lived or who will ever live on this planet has a body. And those bodies are unique. And those bodies are, in a way, a stewardship that we each have. And no one will ever care about your body more than you do. And I certainly care about my body more than anybody else because we're the ones that have to live in our bodies. And when we understand some principles about physiology, then we can leverage those principles to get better results with our bodies. And if we're supporting somebody else, whether it's because we're working in assisted living or skilled nursing or memory care, or we have a family member that we're supporting, or we just have loved ones around us and we want to help them, the more we can understand about some basic physiological principles, the more tools we have in the toolbox to support the people around us who also care about their bodies and want to do something to have optimal health. If you look at the National Center for Health Statistics put out by the CDC, you can find a number of the number of deaths for various causes. And when you look at that list, you see heart disease right at the very top. And then behind it, you see cancer, not that far behind it. And then the number 3 cause of death is accidents. But if we just take out accidents and we keep moving on to stroke and chronic lower respiratory diseases and Alzheimer's disease and diabetes and nephritis and chronic liver disease and cirrhosis of the liver, you find a whole list of things that all have root causes that in one way or another relate to insulin resistance. So increasingly, doctors and researchers are recognizing that insulin resistance, or you might say hyperinsulinemia, too much insulin in the blood, is like the epidemic that nobody's talking about. It's what's upstream from all of these disease states that are killing us. It's interesting if you go back and look in time. In 1900, people on average died younger. So the average age of death in 1900 was kind of the mid to late 40s. And that average was dragged down by women dying in childbirth and children dying of childhood diseases and people that were dying of acute illness and infection. And part of that was because antibiotics weren't discovered until 1927, and it took a long time for different interventions to be developed. But now we have a lot of those treatments, and we have microvascular surgery and all sorts of other things that help us live longer. But if you go back to 1900, you also see something interesting. Heart disease didn't really exist in this country. And it wasn't because people were dying younger. There were still plenty of people that died older. People lived long lives. It's just the average was dragged down by all those other things that killed people at younger ages. But we didn't see so much heart disease. We didn't see as much cancer. We didn't see as many strokes. We didn't see as much Alzheimer's disease. And I know for a long time people have said, well, maybe we weren't diagnosing these things. Well, if you go back to the 1970s, you see that virtually nobody had fatty liver. Unless you were a raging alcoholic, you just didn't have fatty liver in the 1970s. Doctors never saw it. And now 30 to as high as 40% of the Western adult population has non-alcoholic fatty liver disease, which wrecks you metabolically. That's a really bad sign. And that relates to a lot of these problems. It ties in as a comorbidity. So wow, what is going on? If you go back to the 1970s and earlier, you don't see an obesity epidemic. You don't see a type 2 diabetes epidemic. You don't see so many women who can't get pregnant because they have polycystic ovarian syndrome. Something has changed. And I think by the end of the conversation today, you'll be able to see to a greater degree that one of the things that has changed dramatically is that we're a more insulin resistant population than we've ever been. So there is a silent epidemic that's behind all of these diseases. And it's time that we start seeing it, shouting it from the rooftops, helping our friends and family recognize it for what it is, because that gives us power. So let's talk about symptoms versus root causes. If you look at some of these diseases that we've talked about, whether it's heart disease or a disease prone state, an inflammatory state, or Alzheimer's disease, or we look at strokes, or we talk about type 2 diabetes, or obesity, or polycystic ovarian syndrome, or fatty liver, or high blood pressure, or erectile dysfunction, all of those things, and many more that you'll hear about today, are symptoms of the root cause issue of resistance to the signaling of insulin in the body. So hopefully you can see in looking at that that, wow, if we can move upstream just a little bit, if we can identify what is happening that's causing the symptoms called heart disease or inflammation or PCOS or any of these things, then we can do something more about it. So right up front, I want to tell you, number one, how to learn more, and number two, where I can give a lot of credit to for some of the research that I'm going to cite. Dr. Benjamin Bickman, who is a doctor of physiology and teaches about metabolic disorders at the college level and does a lot of research. He has a food lab where he tests different things in tightly controlled experiments. He wrote a book in the last few years titled Why We Get Sick. And he's talking about all of these different diseases as a problem of insulin resistance. And he's got page after page after page in the bibliography of research studies to reference. So it was a really good source for me to turn to where someone has done the work to go look at different studies and figure out what's showing up and try to understand what is affecting our health so broadly. So I highly recommend reading Why We Get Sick if you want to learn more about insulin and its role behind all of these diseases. And I'm basically going to give you almost like a book review of the first half of his book. We're going to go through many of the things that he touches on, and I'm going to give you some highlights. So maybe you can even pick up in the middle of the book and read the second half of it and learn some of the great things that he has to say there. So let's start with some basics with insulin just to get us all on the same page. Insulin is a hormone. It's made in the pancreas, which is tucked away under the stomach. And it's famous for regulating blood glucose levels. I think most everybody knows that insulin has something to do with blood sugar. And if you don't produce insulin because you're a type 1 diabetic and you've had an autoimmune reaction against the pancreas, that's really bad. That's life-threatening. And so you need insulin to be treated for that. But I think the thing that most people don't realize about this humble hormone, as Dr. Bickman would call it, is that insulin actually affects every cell and every tissue in the body. Literally every cell in the body has an insulin receptor, and there's nothing that is not affected by insulin. So obviously we can't go through every single tissue in the body in the course of a 45 to 50 minute presentation and talk about exactly what insulin does there. And there are some tissues where we are kind of infants in understanding exactly how insulin might play a role with it. But I'm going to hit some highlights so that you have a greater appreciation of the fact that insulin does way more than just regulate blood sugar. On the surface, we can go just slightly deeper and understand that insulin regulates how cells use energy. It regulates how they change in size, whether they get bigger or smaller. It influences the production of other hormones. And overall, we need to know that insulin is anabolic. It is not catabolic. Now, those are medical terms, so let's define them. Anabolic means it produces growth. and catabolic means it's breaking something down. So you've probably heard of anabolic steroids that have been abused by bodybuilders for years. Well, insulin is an anabolic hormone, and there are even lots of cases of bodybuilders abusing insulin. I don't recommend that. It's pretty tough on the heart. But for a long time, insulin was more abused than things like testosterone. So just be aware of that. That understanding is foundational to understanding how insulin is going to affect different tissues. It causes growth. So let's then define insulin resistance. When you hear that term, what are we really talking about? Well, as the term suggests, insulin resistance has to do with a reduced response to insulin. But what's really going on is if you don't respond to it as well, your pancreas has to produce more to get the same job done. And that results in a condition that's a better name for insulin resistance. It's more accurate. It's called hyperinsulinemia. So let's break that down. Hyper means too much. If you have a hypermanic episode, then you're really manic. You're really excited. You're all revved up. So too much insulin. And anytime you see the root emia, it means in the blood or something to do with the blood. So if you see the word anemia or someone who is anemic, it means there's something misshapen about red blood cells. So hyperinsulinemia is just too much insulin in the blood. Well, you can be insulin resistant for decades. You can have high insulin in the blood for a long time before you become a type 2 diabetic. Type 2 diabetes really starts sometimes decades before the symptom that is used to diagnose type 2 diabetes. If you're type 2 diabetic, technically in the medical world, then your fasting blood sugar runs really high. Your body can't control your blood sugar. But long before that happens, your pancreas starts having to pump out more and more and more insulin just to get the job done of delivering that glucose into the cells. Why? Because if you don't deliver the glucose, then the cells can't produce energy. And if they're not producing energy, then they don't perform whatever their given function is. So if you're not getting sugar, glucose, into the cells of the brain, then you get symptoms like brain fog or anxiety or depression or ADHD or all sorts of other brain-related symptoms. And if you don't get glucose into the cells of other tissues in the body, then you get symptoms there too. It's unfortunate that we don't diagnose type 2 diabetes until there is major metabolic mayhem that's been going on for a long, long time. So let's talk about insulin resistance and heart disease. I pointed out earlier that basically nobody had heart disease in 1900. In fact, when The Lancet, one of the oldest medical journals on the planet, was trying to bring techniques for treating heart disease to the United States, people were laughing about it, saying, well, we don't have heart disease in the United States. Why do we need to know about this? Well, now we really need to know about it because it's the top killer in the world. So let's consider some principles that have actually been around for a long time. Dr. Joseph Kraft, who died not all that long ago at age 95, is an absolute pioneer in this area, and it's a crying shame that he does not get credit for his work. This is a guy who spent many years writing papers about really good controlled experiments that he did with glucose tolerance tests, where he would give people a bunch of glucose, and then he would follow not only their sugars over time, but their insulin response over time. And instead of following them for a couple of hours, he followed them for many hours. And it was he who said, those with cardiovascular disease not identified with diabetes are simply undiagnosed. In other words, diabetes and cardiovascular disease absolutely go hand in hand. Now, when we're talking about heart disease or cardiovascular disease, we're actually talking about a lot of different conditions, and one person labeled with cardiovascular disease might have slightly different issues than another person, but let's kind of go into some of the nuances here. So let's talk, for example, about hypertension, high blood pressure. Increased insulin equals increased aldosterone. Aldosterone is an adrenal hormone that regulates the balance of salt and water in the body. So it's made in the adrenal gland. And when aldosterone goes up, then you retain more salt and water. Well, everybody knows what happens if you have more salt in a physical system. You also retain more water because where sodium goes, there goes water as well. And what that means is you end up with a greater volume of blood. You have more liquid, so the body produces more blood. And that means you've got more liquid flowing through the same pipes. In other words, you have higher blood pressure. I think often salt gets blamed for what sugar and insulin are doing. And we see it all the time in clients that when they improve insulin sensitivity, when they cut out sugars, and their body doesn't have to produce as much insulin, which means they don't produce as much aldosterone, then they don't retain as much salt, and they have this shifting of fluids. Oftentimes, people that go to a low carb diet, and I'm talking any low carb diet, whether they go vegan or vegetarian or carnivore or a ketogenic diet, as soon as they're dropping out excess carbohydrates and they're not stimulating so much insulin and aldosterone, they lose weight pretty rapidly at first because they're just urinating off all that extra water once they don't retain as much salt because they don't have so much aldosterone signaling. So maybe it's not so much that people need to cut out their salt in a lot of these cases, as much as people need to quit stimulating so much insulin, which therefore stimulates so much aldosterone. So, what about another feature of heart disease, which is thicker blood vessels? Imagine that you have a garden hose and the same amount of water is flowing through it, but suddenly you increase the thickness of the inside of that hose. So you have a much smaller tube for the water to be flowing through. Everybody knows intuitively what happens when you do that because I bet all of us have taken a hose and we've put our thumb over the end of it and we've reduced the outlet that the water's flowing through. And when we do that, then the water comes out with much greater force. That's where instead of just letting the water dribble out, you increase the pressure by decreasing the size of the opening that the water's pouring through, and then you can spray off the concrete or something like that. Well, insulin is our hormone of growth and storage. It causes things to grow, and that includes endothelial tissues. And if you look at this diagram of the various blood vessels that we have in our bodies, you have arteries that carry blood away from the heart. So they're under higher pressure. That's why if you hit an artery when you have an accident, blood's going to spurt out and it's going to be a lot redder than the blood if you hit a vein because there's more oxygen in the blood. It's just come from the heart and it's under pressure. And you'll notice in arteries, you even have this internal elastic membrane that's labeled here. So there's a little bit more elasticity to arteries because we have to pump the blood through at that higher pressure. But common to whether we're talking about arteries or veins where blood returns under a little bit lower pressure to the heart, or capillaries that are little microvessels that are just all over throughout the body, in all three of those types of blood vessels, you have an endothelium, that really thin, one cell thick layer that blood actually is in contact with. And when you have a lot of insulin floating around in the blood, guess what happens to the endothelial layer? It's stimulated by that anabolic hormone to grow, and it gets thicker. And when it gets thicker, then the pressure goes up. So insulin directly causes higher blood pressure. Another thing that insulin does is that it makes it hard for blood vessels to dilate. You're probably familiar with the drug nitroglycerin or nitro. And those of you that work in assisted living or skilled nursing definitely are familiar with this because you've probably had a resident at some point that took nitroglycerin because they had heart or they had chest pain that was caused by constricting blood vessels and higher pressure, and they'd feel that tightness and pressure in their chest. And And sometimes people freak out and they think that, oh, I'm having the big one. The widowmaker has come and I'm having a heart attack. And what they're really having in a lot of those cases is chest pain. Well, when you give someone nitroglycerin, you're giving them a form of nitric oxide. And nitric oxide is just a vasodilator. And all it does is it opens up those vessels so that the blood pressure drops and the pain goes away. Well, endothelial cells produce nitric oxide. And insulin, healthy levels, activates the production of nitric oxide in endothelial cells. So I don't want you to come away with the idea that insulin is bad or good. No, insulin does its thing, and we have to find the Goldilocks zone. Too much or too little insulin are big problems. Things have to be well regulated throughout this system of systems called our physical body. And so when it comes to insulin and nitric oxide, as insulin passes through that endothelium, it stimulates the production of nitric oxide, which allows our blood vessels to dilate. So if our pressure goes up, maybe because we're in fight or flight, when it's time to calm down, that nitric oxide lets the system relax. But here's the catch. What happens when you have really high insulin levels? Well, it turns out that those endothelial cells become less and less sensitive to insulin because their receptors kind of pull back and they say, whoa, you're screaming at me here, insulin, so I'm going to downregulate. I'm not going to be as sensitive to you, which means they're not as sensitive to producing nitric oxide, and you end up with blood vessels that do not dilate very well. Narrow blood vessels are a problem in heart disease. And insulin normally activates a narrowing of blood vessels as part of a fight or flight response. When the sympathetic nervous system kicks in and we go into fight or flight because there's an actual danger, our body elevates our blood sugar and our insulin level goes up because we've got to pump a lot more energy through the body so that all of our organs can function at double and triple time, because we've got to make our muscles do a lot more work. If we're going to have to run away from the bear that's chasing us, then physiologically, it's a really good thing that our blood vessels can narrow, the pressure can go up, we can deliver glucose way faster to the muscles. But when you develop hyperinsulinemia or insulin resistance, then there is this chronic sort of slight activation of that fight or flight response, and the blood vessels narrow chronically. And so you get higher blood pressure as a result of that reaction as well. So when it comes to heart disease, you can see all of these things stacking up. And at the end of all of it, I think we have to step back and say, darn it, insulin is causative for heart disease. And why are we not tracking fasting insulin levels much more closely? I sincerely believe that a fasting insulin should be checked at every primary care visit, and physicians need to really understand the direct causative nature of these types of things that we're talking about. Now, another thing, and just to add one or two more things to the list about heart disease, is dyslipidemia. And some of you that maybe have heart disease or have loved ones with heart disease or have been listening to the conversation around heart disease for a long time know that there's a lot of talk about our lipids, our fats. Things like cholesterol get a lot of airtime when it comes to heart disease. And I think the conversation hasn't been nearly as nuanced as it needs to be. So let's add just maybe one or two more layers of nuance to the discussion. LDL cholesterol has been demonized as quote unquote bad cholesterol. Well, if it's bad, why does the body make LDL? And now that we can measure things more accurately in the body, we know that there's different types of LDL. And measuring those different particle sizes actually matters. But there's two basic patterns of LDL. There's pattern A and there's pattern B. So I want you to think of pattern A as much larger. Pattern B is much smaller, much more dense. So think of a beach ball versus a golf ball. Now, if a beach ball were to roll over a storm drain, You follow along the sidewalk and every so often you come to a storm drain. If the beach ball that you were playing with just rolled down the street and it happened to roll into contact with the storm drain, it would keep right on rolling. But if a golf ball hit that storm drain, bam, it would fall right in. Well, if you send enough golf balls down the storm drain, you're probably going to have a clogged storm drain, and there's a problem there. In order to be pathogenic, in order to cause disease, LDL cholesterol must pass into the blood vessel wall. Now, that's not the only thing that needs to happen, so stay tuned. There's more to the story. But to cause disease, you first have to get that cholesterol actually into the vessel wall. And LDL pattern A just doesn't go into those tiny little rifts and tears in the endothelium very well. Pattern B is what goes into the cell wall. Now, one of the best predictors of LDL pattern B is something that shows up in every regular cholesterol panel. So you don't even have to measure the sizes of all of these different lipids to have a pretty good idea of what's going on. If you look at your triglyceride to HDL ratio, which is something that we do for everybody that participates in the enhanced protocol and they get blood work with us here at A Mind for All Seasons, we do a cholesterol panel. And one of the reasons that we don't have you pay for much more advanced lipid testing is that we know a lot just from looking at your triglycerides, looking at your HDL level, and looking at a triglyceride to HDL ratio. And in general, that ratio predicts size. So if it's less than 2.0, then you have more pattern A LDL. And if it's greater than 2.0, you have more pattern B. Insulin actually also directly signals the liver to make more LDLB. And part of what we think is going on there is that when you're consuming lots and lots of glucose and you have high levels of insulin, then the liver is converting all that extra sugar into triglycerides, which is a storage form of fat. So you end up with these sky-high triglycerides. And if you look at a cholesterol panel and your triglycerides are over 150, let's say they're 500, that's a dead giveaway that you're probably eating a really high carbohydrate diet because the liver will store what it can first as glycogen in the muscles, but that's kind of a small storage tank. And when it can't store more there, then the liver converts those triglycerides, or it converts those sugars into triglycerides. And when a triglyceride is relieved of the fat that it's storing, really what's left behind is a small, dense, damaged LDL particle, pattern B LDL. So then let's talk about atherosclerosis, where you get this stiffening, you get these damaged blood vessels. What's going on there? Well, this is actually the most essential process in the development of heart disease. So I said earlier that cholesterol has to pass into the blood vessel wall in order to cause disease, to be pathogenic. But something else has to happen. Fats and cholesterol also have to be oxidized to be a problem. And if they pass into the vessel wall, they usually don't have to sit there very long to become oxidized. And once they're oxidized, then a certain type of white blood cell, part of our immune response, a macrophage, will come along and it sort of eats the oxidized lipid. Those cells engulf the damaged fat because they're trying to prevent it from oxidizing other parts of the cells. So the immune system is really thoughtful about that. And it says, whoa, we got a problem going on here. Let's send the macrophages. Let's engulf those oxidized lipids to prevent further damage. So this is a good thing, unless this process is happening a lot. Because once the macrophages become engorged, they look under the microscope very foamy. In fact, they're often referred to as foam cells. So think of these scavengers that go try to gobble up these damaged cells, and they just get really full with them, and they turn all foamy. And when they can't eat more of those oxidized fat particles, then they release proteins, signaling molecules in the body, to trigger more macrophages to show up. And that's the hallmark of an inflammatory response in our vessels. So when we talk about having vessels that have inflammation, this is what we're talking about. Now, interestingly, cholesterol gets really blamed for atherosclerosis. But cholesterol, at least according to Dr. Bickman and others, is probably not the real culprit here because linoleic acid is the most readily oxidized fat that we have in the body. Linoleic acid comes from things like canola oil and other cooking oils. It's virtually ubiquitous in our world. Most ultra processed foods are loaded with linoleic acid. And linoleic acid oxidizes so fast that it's a real problem when you have linoleic acid binding to cholesterol, circulating in our system. And then if those small, dense pattern B LDL particles get stuck in the vessel wall, think of it like somebody giving a piggyback to a child. So if I'm cholesterol and I've got one of my kids on my back and that kid is linoleic acid, the linoleic acid gets oxidized first. And then that rapidly causes further oxidation of the cholesterol particle. And when those macrophages show up, they start gobbling all of that up. And we have pathogenesis. We have disease that's starting. We have calcification that starts to occur. So linoleic acid may well be a bigger culprit. And it's probably one of the reasons why when people are cutting out those seed oils and they're cutting out ultra-processed foods, that we have better results. That and we're improving insulin sensitivity when we start reducing a lot of the sources that give us that linoleic acid in the first place. So that's a lot with heart disease. And I spend a lot of time there because that's the number one killer. But let's quickly have an overview of some of the other ways that insulin affects us. So let's talk about insulin resistance and Alzheimer's risk. This is an old study from 1997 published in the British Medical Journal. And it was looking at insulin resistance and other risk factors and how they relate to the prevalence of Alzheimer's disease. And what this study found, I thought was fascinating, that aside from having the APOE4 genotype, so that's nicknamed the Alzheimer's gene, aside from that one factor, which was the biggest risk factor in this study, fasting insulin levels was the strongest predictor of your Alzheimer's risk, fasting insulin. And for those of you who like statistics, the p-value was 0.0004. The closer a p-value is to zero, the more likely it is that this is not explained by any other factor. The more likely it is that this is directly related to what we're talking about. A p-value of 0.0004 is a level that most studies just dream about. A lot of people are looking for a p-value of slightly less than 1 to show, hey, this is really statistically significant. So does smoking increase your risk of Alzheimer's? Absolutely, it does. And it's interesting that you have to oxidize fats for them to cause pathogenesis. For you to end up with atherosclerosis, you've got to oxidize the fats in the cell wall. Well, smoking will increase oxidative stress and you'll oxidize those fats a lot faster. So that's one of the reasons that smoking and heart disease go hand in hand. It's also one of the reasons that smoking and Alzheimer's disease go hand in hand. But smoking is not nearly as big a risk as fasting insulin. If your fasting insulin is lower, then you're also not triggering so many of the problems that would lead to compromised vasculature. Age has often been called the single biggest risk factor for Alzheimer's disease. I don't think that that's really accurate, at least in this study where we're looking at a pretty decent sample size of 980 people. We're seeing that no, age wasn't nearly as big a predictor as insulin resistance. Pretty fascinating, I think. A healthy brain requires insulin sensitivity. If you have decreased insulin sensitivity, then you end up with less ability to take up glucose, which is the primary fuel in most of our brains. And if you can't get fuel into the gas tank, you don't produce engine. So less brain glucose uptake equals less brain energy. And that just means poor brain function. And boy, if ever there was a state that could be called poor brain function, it's Alzheimer's disease. A 20-year study of 10,000 men showed that those with insulin resistance have nearly double the risk of vascular dementia. So it's not just about Alzheimer's. And insulin resistance also means lower dopamine production. Well, that means if you're insulin resistant, you got a higher risk for Parkinson's disease as well. And interestingly, antipsychotics block dopamine receptors, and we see kind of a chicken and an egg sort of scenario going on. If you have insulin resistance, you don't produce as much dopamine. But if you block dopamine receptors, then you also become more insulin resistant. And up to 40% of people treated with antipsychotics develop type 2 diabetes within 5 years. That's a very serious side effect and something that we should not treat lightly. A study of middle-aged women showed that those with insulin resistance were twice as likely to have regular migraines. Now, Dr. Bickman in his book actually talks about many other things that go on in the brain related to insulin, but I wanted to hit just a few of these so that you could get a sense of what it's doing in the brain. Let's talk about a few other aspects of our health before we go to Q&A. What about insulin resistance and reproductive health? Well, the pregnant body actually needs to grow. And insulin is our hormone of growth and storage. So it's very expected in a pregnant woman that their bodies actually develop some insulin resistance because that helps with growth. But what if that gets out of control? If insulin resistance grows to the point that blood glucose cannot be managed, then you get gestational diabetes, which is a serious complication in pregnancy. And there are certain risk factors that make a woman more likely to have gestational diabetes, like you got a family history of type 2 diabetes. Your age can be a risk factor because insulin sensitivity tends to diminish a little bit with age. Your pre-pregnancy weight is a predictor because if you weigh more going into pregnancy, it's likely that you have insulin resistance that's associated with that excess weight. And your ethnicity, if you're Asian or Hispanic or Middle Eastern, you're more likely to have a problem with gestational diabetes because you're more likely to have a problem with type 2 diabetes if you come from one of those ethnicities. If you end up with gestational diabetes, so those of you on this webinar, if you were a woman who had gestational diabetes, you need to know that statistically there's a 7 times greater risk of developing type 2 diabetes later in life. And there are a lot of reasons for that. But if you're aware of that, you can take more action. You can do something to manage that. You can track your insulin levels and be really thoughtful about how you approach it. What about preeclampsia, which is a very dangerous change in kidney functioning? It's one of the most serious conditions in pregnancy. If you have high insulin resistance in the first half of your pregnancy, then you have a much greater risk of preeclampsia in the second half of the pregnancy. And this seems to happen because insulin resistance leads to altered blood pressure for the reasons that we talked about earlier, and that affects blood flow to tissues. Well, if the placenta is not getting enough blood, it signals for more blood by releasing what's called VEGF, vascular endothelial growth factor. Basically, it's a signal to the body to make more vasculature. The placenta is saying, whoa, we're not getting enough blood. You better increase the supply by increasing vasculature. But for some reason that researchers do not yet understand, as the placenta signals with more VEGF, in some women it also releases what's called soluble VEGF receptor, which then sticks to that VEGF and prevents it from working. Well, if you're sending a signal that you need more vasculature and then you prevent that signal from working, you don't get more vessels. And without that blood supply going to both the placenta and to the kidneys, then those kidneys lose functionality. And kidneys do a lot of things in our body, but they're basically a filter. And if they stop filtering, then toxins build up, excess water builds up. You end up with high blood pressure because that water backs up, but you're also circulating toxins, which are arguably the biggest problem associated with preeclampsia. And really the only way to solve this is to remove the placenta and take care of this. So these women end up having very early C-sections in a lot of cases to remove the baby as soon as they can, get that placenta out of the body, and try to correct this issue. What about the most common cause of female infertility worldwide? Polycystic ovarian syndrome. The rates of that have just skyrocketed as rates of insulin resistance have skyrocketed. It now affects more than 10 million women worldwide. And insulin is the direct cause of polycystic ovarian syndrome. Period. End of story. When you improve insulin signaling, you can make this problem go away. The ovaries are very insulin sensitive, and ovaries respond to excess insulin by inhibiting what's called aromatase. Now, if you didn't know it, ladies, or gentlemen for that matter, women have a lot more testosterone than estrogen if they're healthy, because estrogen is made from testosterone. Estrogens are made from androgens, and they do that through the process of aromatase. So aromatase allows the body of these women to convert testosterone into estrogen. Well, if you have excess insulin and you inhibit aromatase, then you end up with too much testosterone and not enough estrogen. And if you don't have a mid-cycle estrogen bump, which is what triggers ovulation, then the ovaries retain and they start accumulating those eggs. And then insulin may also directly act on the brain to block the normal luteinizing hormone production. And luteinizing hormone triggers a lot more of what needs to happen in the middle of a woman's cycle. So things just crumble for these women and they end up with ovarian cysts, and it's incredibly painful. And because insulin is a hormone of growth, those ovaries are also swelling and growing under direct influence of that insulin. So whatever a woman does that improves insulin sensitivity causes these symptoms to go away. That's why you will hear women say, I went on a carnivore diet and it solved PCOS. Or I went on a keto diet, solved PCOS. Or I became a vegetarian and it solved PCOS. There are all kinds of ways that we can reduce insulin signaling and improve insulin sensitivity in the body as long as we're cutting out carbohydrate. What about men, though? What about insulin and men's reproductive health? We're not going to spend as much time here because insulin affects women so much more, I think. But men with higher body fat have lower testosterone. And interestingly, fat cells also have aromatase. And if you have high insulin, men, it leads to high body fat, which leads to higher levels of aromatase, which causes our bodies to really aromatize our testosterone into estrogen. It's very common that I see middle-aged men who start crying at Kleenex commercials. And it's not because they're getting more sensitive in their older age just because of life experience. Certainly, I think life experience can help us appreciate things at a deeper level and learn to practice kindness and things like that. But I think a lot of times what's going on is that these guys have developed these very big bellies that have lots of aromatase in those fat stores, and they have super low testosterone because they have so much aromatase. And they're aromatizing all that testosterone into estrogen. And if you give a guy a lot more estrogen, he's going to cry at Kleenex commercials. Men with insulin resistance also have increased risk of erectile dysfunction. And erectile dysfunction is likely one of the earliest symptoms of insulin resistance. Remember that insulin resistance leads to poor nitric oxide production, which means poor vasodilation. And for the penis to become engorged with blood when a man is aroused, you have to have good nitric oxide production. So that's a very early signal. What about insulin resistance in cancer? Well, cancer is a disease of uncontrolled cellular growth. And insulin's the hormone of growth, so it's going to pour gas on the fire. Cancer cells, we have known for over 100 years through the work of Otto Warburg, also rewire their metabolism, and they get their energy exclusively from sugar. And they do it without using mitochondria and without oxygen. So instead of this oxygen reduction reaction that normally takes place, you get fermentation of sugar. You get this very primitive response in the cells. And sugar and high levels of insulin just feed that. So the cells rapidly grow. And a cell that's totally dependent on glucose, that's primed to just ferment that sugar and grow rapidly, is going to thrive in an insulin rich environment. People with hyperinsulinemia have roughly double the likelihood of dying of cancer. And the average breast cancer tumor has 6 times more insulin receptors. Well, that's a recipe for disaster. If men have insulin resistance, they're 2 to 3 times more likely to have an enlarged prostate. And a lot of doctors are increasingly starting to think, oh, benign prostatic hyperplasia, BPH, enlarged prostate, is probably just insulin resistance in the prostate. Men with high insulin resistance are 250% more likely to develop prostate cancer. Well, that's a compelling reason to really be thoughtful about insulin in our bodies. How about just a couple of other things, and then we'll go to some questions here. I noticed there's some things in the chat, and I'm eager to talk about those things. Let's talk a little bit about skin, muscles, and bones. So there's a condition called acanthosis nigricans, which for some people is the first sign of insulin resistance. And it involves high insulin activating melanocytes. The cells that produce melanin are pigment in our skins. And this can show up regardless of your skin type, regardless of the pigmentation that you have. But when those melanocytes are overactive because insulin is anabolic and it stimulates them to be overactive, then you get a lot more production of melanin, and especially in areas where there are folds, like at the base of our neck, like you see in this picture, or in the armpits, anywhere that the skin is rubbing together, those melanocytes are also rubbing together, and there's a lot more activity of all of this, and you end up with these dark patches on the skin. That's a sign of insulin resistance. Skin tags, these little bumps that are frequently seen, again, in those folded areas where you see that discoloration, the acanthosis nigricans, that's a problem of hyperinsulinemia. It stimulates growth and division of the cells that are giving us structure to the skin. What about psoriasis? It's a chronic inflammatory disease. And you get skin that looks like what you see on the picture there, reddish or pink skin. There's the white, silvery kind of scaliness on the skin. You see it on the elbows, the knees, even the midsection. Well, people with psoriasis are nearly 3 times more likely to be insulin resistant. This seems to go hand in hand in a lot of these cases. What about insulin and muscle function? Well, by the time we're middle-aged, muscle makes up 25 to 30% of the tissues of our body. And muscle is the largest insulin-sensitive tissue in the body. More muscle means that we have more of a place to store glucose. So if we have more muscle mass, then we are more insulin sensitive as a general rule. If you're insulin resistant, it compromises healthy muscle function, and that potentially leads to muscle loss. And if you're insulin resistant, and let's say you want to turn things around, well, insulin is anabolic. It allows us to grow muscle. So paradoxically, if you're resistant to insulin, it's actually harder to gain new muscle. And so that's problematic. What about bones and joints? Well, bones are protecting our organs. They're storing minerals. They're making red and white blood cells. In other words, muscles do a lot more than just provide structure and form to the body. They perform a lot of functions, some of which are not all that well researched yet. But osteoblastic activity and osteoclastic activity have to be in healthy balance. All that means is osteoblasts, think blasting off. We're growing something. We're going places. Osteoblasts are about bone cell production, and osteoclasts are about breaking down bone cells. If we didn't have a balance between making bone cells and breaking down bone cells, then we would get an imbalance, and we would either make bone faster than we should, and we'd end up looking like Andre the Giant, who had a problem with his pituitary where he made bone cells faster than he could break them down. So he became really big and misshapen. Or you have osteoporosis, where you're losing bone cells faster than they're being formed. Osteoclastic activity outpaces osteoblastic activity. Well, insulin, not surprisingly, as our hormone of growth, stimulates osteoblasts. If people have insulin resistance, they might have normal bone mass, but they don't have as strong a bones. And if you have a further problem where chondrocytes, those are cells that help us produce cartilage, they require insulin sensitivity to function. And if you're insulin resistant, you might not produce enough cartilage cells. And so your joints start to break down a lot more if you have issues with hyperinsulinemia. Lastly, we'll just talk about a little bit about GI and kidney health. So let's talk about liver, gallbladder, pancreas, those kinds of things just for a minute. All of those organs have to work together in a complex symphony to allow us to digest food. And insulin resistance can create problems in all those areas. And I'm not going to talk nearly about exactly what happens in all of these organs. But consider that insulin resistance, independent of all other variables, can increase your risk of acid reflux by 15%. Well, that's a common issue with the GI tract. And if you develop something like Barrett's esophagitis, yeah, you can live with that, but it also increases your risk of things like throat cancer. So that's you're on the wrong pathway there. Diabetes is a common cause of gastroparesis because of damage that can happen to the nerves. Elevated blood sugar damages nerves. Well, gastroparesis means you can't move food through the gut very well. And if that happens, toxins build up. You develop all sorts of problems with gastroparesis. And we also see a lot of people that have insulin resistance having a lot of problems with leaky gut. Insulin resistance is the strongest predictor of non-alcoholic fatty liver disease. And in insulin resistance, insulin no longer tells the liver to take in glucose and store it as glycogen. Instead, it's breaking down glycogen and it's releasing more of that glycogen back into the bloodstream, which just further exacerbates the problem. So, those are just a few of the things that are going on, not to mention the fact that you end up with dyslipidemia. And so your fats in the blood are dysregulated, your cholesterol panel's way off when you have insulin resistance, and you also end up with hyperlipidemia, too much fat in the blood. Well, what happens when you have too much fat in the blood? Well, one thing is the gallbladder really struggles. You get more of a sludge building up. You're more likely to have gallstones if you've got too much fat pushed into the blood because you're insulin resistant. So, as you can see, there are a lot of things that take place physiologically, and I can assure you we've only scratched the surface. But I hope that you will never see insulin the same way again after today.